Another day, another challenge in Advent of Code 2024. As you can see, we've already done 6 challenges, 2 challenges per day, so today we're going to look at day 4. And as before, I'll be doing these challenges in Funciton, an esoteric programming language that I invented. It consists of lines and boxes which are created using Unicode characters. Day 4, Series Search. As the search for the chief continues, a small elf who lives on the station tugs on your shirt. She'd like to know if you could help her with her word search, your puzzle input. She only has to find one word, Xmas or Christmas. This word search allows words to be horizontal, vertical, diagonal, written backwards, or even overlapping other words. It's a little unusual though, as you don't merely need to find one instance of Xmas, you need to find all of them. Okay, here are a few ways Xmas might appear where irrelevant characters have been replaced with dot. The actual word search will be full of letters instead, for example like this. Okay, and all of these letters are X, M, A, or S. In this word search, Xmas occurs a total of 10 times. Here's the same word search again, but where letters not involved in any Xmas have been replaced with dot. Okay, take a look at the little elf's word search. How many times does Xmas appear? Now that's an interesting challenge, and I can think of multiple ways of doing this. It would certainly be possible to do this with the regular expression engine that I wrote, but I would kind of feel that I would just be shoehorning it onto this problem. I think I want to do this a more geometric way. I want to represent positions in the grid as x and y coordinates, so I could do that using 2 tuples, but I could also do that with an index from 0 to the size of the grid, and then use modulo and division to get the x and y coordinates. So I think I'm going to implement this in a way similar to what would be a nested for loop in a normal programming language, where the outer for loop goes through every position in the grid, and then for each position in the grid, you have an inner for loop which will check each of the 8 possible directions. And then for each position, you would have yet another nested for loop that goes through the 4 letters, X, M, A, S. But that means that we could go off the edge of the grid, right? You could start, for example, in the second row and go up, and then you would hit the top edge of the grid. So I think I am actually going to use 2 tuples to represent positions in the grid, so that I can reliably recognize positions that are outside the grid, because the x or y coordinate could be negative. But besides that, I think I'm going to represent the entire grid of letters as a single string, because that makes it really easy and fast to index into it. So I want to start by reading in the standard input, but that's going to consist of lines of text, which are separated by new lines, which is character number 10. So we're going to split the standard input at every occurrence of the new line, and that will give us a lazy sequence of all of the lines of text. And now I need to determine the size of the grid. I'm going to assume that every line is going to have the same width. So I'm just going to determine the length of the first string, that will be the width, and the number of strings, that will be the height. To get the number of lines, I can just apply the count function, but to get the length of the first line, I first need to obtain the first line. Since this is a lazy sequence, which is a lambda expression, we're just going to call that lambda expression. That's going to give us the head and the tail, and the head is the first line. And that first line, which is the head, is going to be a string. So instead of the count function, which is for lazy sequences, we now need to apply the string length function. And we don't really care about the tail here, because we only needed the first element to get the width. Now, I said that I would represent the entire grid as a single string, and the best way to do that is to just join up all of the strings that constitute the lines of the input with the empty string as a separator. The next thing we need to do is something like a for loop, but Funciton, being a functional programming language, doesn't do loops. Instead, we do recursive functions. So I want to write a recursive function which will take this information that we have, the width, the height, and the grid, and then some running number, like the iteration variable. But then we run into the issue that that is 4 values, and Funciton can only do up to 3 inputs per function. So I'm going to wrap the width and the height into a single value by turning it into a lambda expression which returns those 2 values. And that lambda expression doesn't care about its input, so we silence that. And then we can pass those 3 values into our hypothetical recursive function, which we haven't written yet, which is the lambda expression containing the width and the height, the grid, and then 0 as the first value of our iterative value. Now I expect that function to just count up all of the occurrences of Xmas, so it will come back with the total, and we want to output the total on the console, so we need to turn that into a string. And with that, I think we have our main program done, and now we just need to write that function, which is going to embody the outer for loop, so we're going to have more functions for the inner loops, but let's do the outer one first. So let me start by creating a declaration box. Let's not lose track of our parameters. The first one here is the width and height lambda expression. The next one is the grid as a single string. And then the next one is our iteration variable, which I'm just going to call I. We will need to unpack the width and the height, so let's call the lambda expression here to obtain those two values. And since that lambda expression ignores its own input, it doesn't matter what we put in, so I'm going to put in 0. Now, what is the termination condition going to be for this for loop or for this recursion? Well, it's when I has reached the end of the grid. And the end of the grid is, of course, w times h, because there's going to be width times height many number of characters. Which means that in order to check if we're done, we would need to compare I against w times h. But if you think about it, that would mean that we are multiplying w times h over and over again at each iteration of this function. So I think I'm going to change the call to this function, and I'm going to pass in w times h minus 1, and then instead of incrementing I, I'm going to decrement it. So in other words, I'm going to start at the bottom right end of the grid, and I'm going to work my way up. The number of Xmas's in the grid is going to be the same. It doesn't matter which order we go through them. Now, taking a copy of the width is not hard. I can literally just turn this into a splitter, and then we have another copy of W here. But the H is here, so we need to somehow get a splitter into here. So let's shuffle things around accordingly. So now we've got W and H here, so let's just multiply the two. And we want the third input to our function to be W times H minus 1, so we need to decrement it by 1 and then pump it in there. Perfect. Now the third parameter that we have come out of here is an iteration variable that starts at W times H minus 1, and we're going to keep decrementing it until it reaches -1, because 0 is still a valid position in the grid. It's the top left corner. And this parameter here is the grid, so let me just move that down and put an arrow there. Now I'm going to scroll down a bit, and I'm going to start writing some code here in order to express the terminating condition. So we want to check if I is less than 0. So if I is indeed less than 0, then... oh wait, this is wrong. This is the wrong way around. So I'm going to fix that by making that a greater than. So if 0 is greater than I, which is the same as I less than 0, and then we can use the interrobang function because greater than is always going to return a boolean. So if that is true, then we need to do the processing. We need to find out how many Xmas's there are in this position, and then we need to do the recursive call for all the previous grid positions. But what if it's false? Oh, wait, it's the other way around. If I is indeed less than 0, then we're done. Okay, so I'm going to change this again, this time to less than or equal to. So if 0 is less than or equal to I, which is the same as saying that I is greater or equal to 0, then we need to do some processing. Otherwise, we are done. And done means that there are no further Xmas's, so we're just going to return 0 here. Okay, so far so good. Now, in the true case for this question mark, we need to do two things. We need to find out how many Xmas's there are in this position. So we're going to call another function for this. And then we're going to check how many Xmas's there are in all the grid positions before it. So we need a recursive call for that. And then we need to add up the results of those two. So let's start by putting an addition function here. And you know what occurred to me now is that I don't think we need the H anymore. We only needed the H once, let me scroll up, to calculate the size of the grid, and then we just start at the end of the grid. The only reason we still need W is because we want to use division and modulo to turn I into X and Y coordinates. So I think we can save ourselves this entire lambda expression if we pass in only the W. So let's start by getting rid of the lambda expressions in the main program. And then let's streamline this a little bit so there are fewer kinks in the wires. So now the three things that go into this function are just the width, which we get from the length of the first line of text, and then the grid as a single string, and of course the size of the grid minus 1. So we can now get rid of this entire thing here and assume that what comes out of here is literally just W. Coming back to the code that we have down here. So what did we want to add? We wanted to add the recursive call to this function. Let's start with that, because that should be relatively easy to do. In order, the parameters are the width, which doesn't change, and the grid, which also doesn't change. But then this here needs to be I minus 1. On the other side, we now need to call that new function, which we talked about. Now that function, I think, needs 5 different things. Let me just write them all down. It definitely needs the whole grid. It needs to know the width of the grid so that it can tell if the x and y coordinates are out of range. It needs the x and the y coordinates. And it needs the set of directions to look in. I'm just going to call that dirs for now, but it's going to be a list of tuples. And the tuple is like the amount of displacement in the x and the y direction. So for example, for the up direction, you're going to make no change in the x coordinate and you're going to go -1 in the y coordinate, because up, right? And then you're going to have, like, for example, 1, -1 is going to be up and right. And then the next one is going to be just to the right. So we're going to move forwards in the x direction and 0 in the y direction, etc. And we're going to have 8 of these. Now, actually, I don't think we need x and y just yet. I think we only need those in the innermost for loop. This is the second level of the 3. So I think I'm going to turn that into I again. So if I'm not mistaken, I think I do actually need to pass 4 different things into this function, which I can't do. So I have to turn 2 of them into a tuple. So I think I'm going to put W and I into a lambda expression. So that's a single value. Okay, now let's think about how we're going to represent that list of directions. In fact, let's start by writing down what they actually are. Now, I'm going to represent this whole thing as a single list of these 16 values. And then every iteration of this function is just going to take off the first 2 and regard them as delta x and delta y. In other words, the amount of change in x and y. So that means that we need to find the integer encoding of this entire list and pass that in as a constant. In order to do that, I would like to write a helper program, which I can just pass some string on the command line, which is a comma-separated list of values, and have it generate the list for me. So let's start by reading standard input. Now, I don't want to set in stone that the comma is going to be the separator. So I'm going to make it so that the first character of the standard input specifies what the separator is. So let's take a copy of the input and determine the first character in one copy and the rest of the string in the other copy. And then the next thing we want to do is to split the rest of the string, which is what comes out here, by that separator. So I'm going to use the string split function for that. And now I have a sequence of strings. Now I will sometimes want to encode a list of strings. Not in our case today. I need integers now, but I want to be able to encode strings. So I'm going to put in the ability to specify which of the elements are going to be strings and which ones are going to be integers. And I'm going to make it so that if the first character of one of the substrings is a hash symbol, it's going to be an integer. And in all other cases, it's going to be a string. So we need to map over the list of strings that we've just obtained. And then we need to do something very similar as we did here, don't we? We need to obtain the first character and the rest of the string. And we want to compare that first character against the hash symbol, which happens to be Unicode character 35. Now, if it is a hash character, I need to convert the string to an integer. And if it is not, then we just want to use the string directly. And then the output of that question mark needs to go into the lambda expression output. The map function doesn't care about the second output of the lambda expression, so we just put 0 there. And now we have a lazy sequence of the values that we want come out of here. We want to convert that lazy sequence into a list. And remember, we have all of the library functions listed on the ESOLangs wiki page, and indeed, there is a function to convert a lazy sequence to a list. So we're going to use that, and then the result of that is going to be a single integer, but we want to output that to the console, so we need to convert it to a string. So let's see if that helper program works as expected. Let's start by calling it on an input that starts with a comma, which is our separator, and then the number, 47. In other words, we have a list consisting of just one element, and that element is 47. and I get an error. And the error that I get is value was too large or too small for an int32. What is this about? Funciton doesn't use int32, it uses big integers. Well, let's pay some closer attention to what it says here. It is trying to evaluate a shift left node. And the amount by which you shift does get converted to an int32, because, when do you ever want to shift by more than 4 billion bits? Come on. So the mistake in our program is that we have this the wrong way round, and since we copied and pasted it, it means this is also the wrong way round. Right, this is the output, which means that this is the first operand. So this is actually shifting -1 by the amount of whatever the string encoding of our input is, which is humongous. So I need to swap the order of the operands, and I'm going to do that by just putting the output on the other side of that box. Version number 2, let's see if that works. So let's just run the same command again, and this time we do get a value out. Now let's see that it also works with numbers, so if I put #0, I expect the number 2, I think, is what encodes a list containing just the 0, and that's not what we're getting, so we made a mistake. And the mistake that we made is that I shifted the string by just a single bit, but I wanted to shift it by 1 character, which is 21 bits. So let's try that once again, and this time we get the number 2. So now if I take 47, for example, we get this. Now, make no mistake, this is actually the string containing just the number 7, because what I forgot is that I am taking away the first character even if it isn't a hashed character. So this will just take away the 4 and encode just the 7. If we actually wanted the string 47, we would have to put some other character in front. But that's not what we're here for. We're here to encode integers, and specifically we want all of these integers. Let's see. Now I have to assume that this is correct, so let's just put that in the clipboard, and let's get back to our Advent of Code thing. Now the number that I got out is this monstrosity of a number here, but the thing is we don't know what order we want these arguments in. We should probably write this function first and then see which geometry is the most convenient. So let's start by doing that. So I'm going to copy this declaration node and I'm going to put it down here. I'm going to replace the function name. And now let's scroll down and then think about what we need that function to do. Well, we're passing it a grid, a lambda expression containing a width and an integer, which is the positioner grid, and this list. So the first thing that we should probably do is check if that list is empty, because we're going to be chopping off the first 2 integers, which are going to be a delta x and a delta y, and then we're going to pass the rest of the list to the next recursive call until it reaches the empty list. So let's start by writing a question mark box to check if the list is empty. And what do we want the function to do when the list is empty? Well, there are no further xmasses to find, so we're just going to return 0. But in all other cases, we now need to check if the letters in that direction form the word XMAS and don't run off the edge of the grid. Well, we now have an I, which we can turn into an x and a y coordinate. We have the dirs list, which we now know is not empty, so we can chop off the first 2 elements, and that will give us delta x and delta y. But then we also need to do the recursive call of that function in order to process the rest of the directions, and we need to add those 2 results. So let's put another addition box right here. And just the same as over here, I think the recursive call to that function is going to be easier to implement, so I'm just quickly going to do that. And as for the other operand to the plus, well, we now need to check whether we actually have XMAS. And I know I said earlier that I'm going to have a 3rd level for loop in there, in other words, another recursive function, but I think I've actually come up with a better way. What I'm actually going to do now is I'm just going to create a lazy sequence of all of the characters in the grid, starting from that point in the direction given by the first 2 elements of DIRS, and then I'm going to truncate that sequence at 4 characters. And then I can just compare the result of that against the string xmas. If the sequence runs off the edge of the grid, it'll give us a shorter string, so it'll never be xmas. And if it encounters any wrong letters, then it'll also not be xmas. So that means that ultimately we want to compare the string against xmas, which means that we want a comparison operator here, which will return 0 for false, which is what we want, but it'll return -1 for true. But this is also the only time where we generate a value that we end up adding. Everything else here is recursive calls, all of which will eventually come back to this comparison. So we will end up adding lots and lots of negative ones, which means that at the very end of all of this, we're going to get the negative of the result that we wanted. So why don't we scroll back up to the program and remedy this by just putting a unary minus at the very end. So that should fix that discrepancy and give us a positive result. So let's go back to the function. Now, in order to know what to compare the string to, we need to encode xmas as an integer. And you know that I have a helper function for that. I can just run this str to int tool and I'll get this number, which is the integer encoding for xmas. Now, what are we comparing against this humongous number? Well, remember, we want to extract letters from the grid and then join them all up into a single string. So we need the join function. And we want to join them up with no separator. And now what needs to come in here is the lazy sequence of the characters that we obtained from the grid. And we're definitely going to implement that with a map function. What do we want to map over? Well, we are going to extract up to 4 letters. So let's just take the sequence of integers from 0 to 3. And the second argument to the map function is going to be a lambda expression. And now let's scroll up a little bit. So we have a lambda expression, and the input to that lambda expression is going to be one of these integers. So it's the amount of steps that we go forward from the starting location, which is I. You know, let me actually document the names of the arguments that we have here, even if we don't know their order. We have a lambda expression that will return w and I, we have the entire grid, and we have the directions list. Now, I is the position in the grid, but we're going to turn that into an x and a y coordinate. So let's pretend like we already have the width and the x and the y coordinate. So what comes out of here is a value n, which goes from 0 to 3. And from that, we want to calculate the new x position, which is going to be the x position at which we start, plus n times the delta x, which is the first value that we got from dir. So let's write that down. We're going to obtain the first 2 elements of this, and we're going to call that delta x and delta y. And of course the same for y. Let me space that out a bit. Y plus n times delta y. Now the map function doesn't care about the second output, so let's just put a 0 there. But the first output here needs to be the character at the relevant position in the grid. But remember that we could be outside the bounds of the grid. So we actually need to make sure that our new x and y position is in range first. And we need to check that for both the x and the y. So I'm going to use a logical AND to connect those 2 conditions. Now we can safely assume that if either x or y is not in range, then we want to return no character at all, in other words, an empty string. So I'm just going to return 0 here. And before I forget, this is of course not the original x, this is in fact that expression. So let me just quickly replace that. Now, how do we check if something is in range? Now, looking once more at the ESALang's wiki page, I'm going to use this in-range operator. And I'm going to use the min-inclusive, max-exclusive variant so that I can just pass in 0 and the width, and it will check if it's between 0 and width minus 1, which is what we want. So let's put a call to that range function right here. And the arguments go in the order lower range, then the value, and then the upper range. And the value is this coordinate. The lower bound we said is 0. And the upper bound is literally just the width. We don't really need this annotation anymore. Now, to check if y is in range, well, we don't have a width equivalent. That would be the height. We don't have the height. But here's the thing. We actually only need to check that y isn't negative. As long as y is at least 0 and we know that x is in range, it means that if we try to obtain a character from the grid string that is beyond the size of the grid, we'll just get an empty string anyway. So we don't need to check if y is too large, only if it's too small. So let's check if y is greater or equal to 0. And now we have reached the true branch of that question mark. So we need to index into the grid. And the specific index that we want is we need the new y coordinate, which is y plus n times dy. And then we need to multiply that by the width. And then we need to add the new x coordinate, which we now know to be in range. So it's not going to go off the left or right edge of the grid. So we need to obtain a character from grid, and I'm going to use the substring function for that, and I'm just going to pass 1 as the length. So let's add a call to the substring function. The first argument is the string that we want to index into, which is the grid, and the third argument is the length, so let's put a 1 there. And before I continue, I noticed that I forgot to calculate the correct y coordinate here, which is y plus n times delta y. So here we want to add this value and this value. So let's start by putting an addition. And on one side of the addition, we want to add this one. Now I could add that either on the top or the bottom, but I think I'm going to add it on the bottom because then I can punch through these two wires and connect it up with this other occurrence of that same expression. On the other side of that addition function, we want to add this, which is itself a multiplication with w. So let's put a multiplication box there. And this grid thing here is in the way, so I'm going to put a wire crossing function there. And then we can directly join that up with the other occurrence of that same expression. Finally, the other side of that multiplication is simply w. I just randomly noticed that I mistyped this here, so let me quickly fix that. Now let's write these expressions here. So both of these are an addition, so let's put a plus box on both sides. And on one side of the plus, we want a multiplication with n in each case, so let's put a multiplication box on both sides. So here we have y come in here at the bottom, and then up here we'll have n times delta y, and then down here we'll have, well, let's say n goes in here, and then this would be delta x, and then this would be x. And these are the only times that we actually need the n, which comes out of the lambda expression here. So let's join that up now. Okay, now we don't need this anymore. And now let's think about how to obtain dx and dy. We want to take the first two elements of dirs, and the first one is going to be dx. So I'm going to do the dy first, because that is going to be the last result of a shift operation. And then the rest of the dirs is going to come out here, whereas what needs to come in here is the dirs list with the dx removed. So we're going to put the other shift operation up here. And ultimately what goes into this function at the top is dirs. So now let's think about how we get x and y. But we also need a copy of w here, so this is going to be a bit tricky. Well, x and y are actually the remainder and the quotient, respectively, of dividing I by w. And we happen to have a connector for w here, so we need to pass w into here anyway. So let's do the division modulo inside of this space. We want x to be the remainder, so let's put the division function right here. And we want y to be the quotient. So if this is the remainder, then the quotient is going to come out here, so we can connect that directly. But now we need to get w into here. So I'm going to punch through this wire, and that requires me to pull everything apart a bit. And then we can just use a bunch of y-crossing functions to liberate the w and the I from there. We still need to extract the w and the I from the lambda expression that we get as a parameter. And w and I are in a very convenient spot here, so I think I'm going to do that right here. No, wait, I still need w over here. So let me connect up those two w's first. So now if I haven't made a mistake, this is where that lambda expression with w and I needs to go in, and this is an input that it doesn't care about, so let's just put a 0 there. And now that I can see the order in which grid, dirs, and that lambda expression occur, I think I'm going to put that lambda expression on the right end, so it's the third argument, and then the dirs I'm going to put on the bottom, so it's going to be the second one. So let's actually, we don't need this annotation anymore. And then grid is going to go on the left. And now all that's left to do is to join these all up with where they need to go. In particular, dirs needs to go not just here, but also down here where we're checking if it's empty. But then of course we also need to do the recursive call. So now that we've decided on the order of the parameters on this, we can put them here. So we want this to be the grid, and that doesn't change, so it's still the same grid as before. This needs to be the rest of the directions. And then the last one is the wi lambda, which also doesn't change. And I'm going to start with dirs. So I'm going to move the declaration box all the way to the right, and then I'm going to connect up both of the occurrences there. Next, we can connect up grid with both of the occurrences that need it. And once again, the function is getting too large to fit on the screen, so let me zoom out a little bit more. So let me scroll up a little bit, and now all we need to connect is that wi lambda, and finally the rest of the directions list. Okay, that is the innermost recursive function done. Now let's scroll up again, and let's zoom in again, and we should now put these arguments on that invocation of the function in the correct order. We know that the first one was the grid, the second one is the directions list, and the third one is the wi lambda. Now, as for that wi lambda, we can immediately write it right here. Now, I kind of regret already having decided the order of these, because now I'm gonna need quite a few wire crossing functions to deal with that. But that's okay, I can do that. Let's start by connecting up the the indexes. And the W's are easy to connect as well because we can route it around the top of the function. And now we can connect up grid with only one wire crossing function, so let's do that. And now I realize that I forgot about one of the i's, but fortunately that's not a big deal because I can just punch through this wire here. And I can save space by reusing a 0 to make that work. And finally, all that's left to do is put this humongous constant, which is the list containing the direction values, into here. Now, this just so happens to be exactly 50 digits long, so I'm going to split that into 5 lines of 10 characters. Okay, if I haven't made a mistake, then that is the outermost recursive function, and we're done with the main program as well. So let me zoom out of the whole thing, let me put the first recursive function to the side here, and then we should be able to zoom out far enough to put everything on the screen. So, I haven't had an opportunity to test any of this, but here we go. This is all of the code that we wrote, and now I'm going to run it, and there's probably going to be tons and tons of errors. Attempt number 1. I'm going to run this with the example input from the puzzle description, and although it took longer than I expected, I am getting an 18, and looking at the puzzle page, that is in fact the right answer, so to my own surprise, first try! Now, since that already took a couple of seconds, I fully expect that running it on the full puzzle input is going to take a very long time. So I'm going to have it measure the time, and I'm going to put a cut in the video here so you don't have to wait this long. 19 minutes later. And we're back! And it turns out that it took 19 minutes and a few seconds to process the input file, which by the way is a 140 by 140 character word search. And of course I'm getting an answer, which I'm going to paste right here on the bottom of the puzzle page. And it says that's the right answer! Perfect! We're 1 gold star closer to finding the chief historian. Okay, so that means we have 7 stars now, out of 50. Still quite a lot to go.